Hello, my name is Alvaro Soto, and I will talk about my computer architecture.
Over here, we got the block diagram for my computer architecture. We got the main components over here, like the program counter, the memory system, the instruction register, the register array, and the ALU. Also, we have a sequencer which sends all the control signals to each of these entities. In this architecture, we can go from instruction to instruction sequentially, we can branch, or we can jump. For that, we have a mux that selects which signal to pass into a program counter. Also, once we get the data from the memory, the instruction from the memory, we store into the instruction register. Once we have the instruction in the instruction register, we send the signals to all the places that it needs to go. For example, like the sequencer, the register array, this part over here where we sign extend certain bits so we can do a branch.
Next is the clocking scheme. For this architecture, we perform the changes in the finite state machines in the sequencer on every falling edge. While the clock is low, the control signals in the CPU get propagated. And on the rising edge, after all the signals got propagated, we perform the destructive actions.
As previously mentioned, this is a 16 register approach. Something interesting about this architecture is that I have dedicated registers for I/O purposes. For example, register I0 is used to read from the I/O control register, and register I1 it holds the value to perform the operations on I/O. Also, something interesting about this architecture is that the load and store instructions have dedicated registers. So for example, the load instruction has register L0. In this register, once the load instruction is done, the data that got read from memory will be stored here. On the other hand, on the store instruction, the data that needs to be written into memory will be in this register, S0. Next up are the types of instructions. We have three types of instructions format. The first one is the F type, which has 4 bits for the opcode, 2 4 bits to specify the registers, and one last 4-bit for the function code. For this type, we have two overloaded versions. One version is the F-type jump. In this version, the last 4 bits of the func field are don't cares. The other version, which is the F-type overloaded, uses the RT4 bits as immediate value bits, and it keeps the func field bits. This type of overloaded version is mostly used for the shift left and shift right instructions. The second type of instruction is the M type. This one has 4 bits for the opcode, has 4 bits for the register, and then finally 8 bits for the immediate value. Finally, the last type is the B-type instruction. This one is mostly used for the branch instruction. It has 4 bits for the opcode and 12 bits for the immediate value. The code convention is the following. For ALU operations, the opcode will always be 0000. Now, for anything else that is not an ALU operation, it will start from 0001 to 1001. As of right now, we have 18 instructions. We have an addition, subtraction, exclusive OR, bitwise logical AND, bitwise logical OR, shift right logical, shift left logical, set on less than unsigned, multiply, add immediate, subtract immediate, OR immediate, low upper bits immediate, load word, store word, job and link, branch on zero, and branch immediate. Now my assembler. It was done in Java and it has a couple of nice features. For example, the multiple directives that it supports. It supports the equal directive, the ASCII directive, and the include directive. Also, the comments that it supports are the numeric symbol. So my assembler takes one file and it converts the file, the txt file, into a MIT file. To do that, we gotta type Java assembler and the path to the txt file. If the file is good and it doesn't have any errors, it will create a MIT file on the root directory, which is here, and it will output the contents of the value on the console. On the other hand, if the value is invalid, it will not output a MIT file and it will output the error lines on the console. So for example, if the file is invalid, we can just run it and it will give us an error message and what the error is, and it will not create a MIT file. Now, my emulator can take a MIT file and emulate it. It can simply emulate it or it can debug it. To do that, we run Java emulator and the name of the MIT file with space -d for debugging. It outputs the original line, the instruction value, and the PC of the instruction, not the PC incremented, the PC of the current instruction that just got emulated. It also displays the registers after execution, and it gives you a few options like step next, terminate. You can just run it, revert one step, restart, or you can put a breakpoint. If you put a breakpoint, you have to provide a line of where you want the breakpoint to stop, and it will stop at the first coincidence of that line. For example, if we put a 0, it will stop right there.
For my computer architecture, I implemented two features. The first one is the hardware multiply. It is faster because it only takes 4 gate delays in one instruction time. On the other hand, the binary multiplication, at least, it takes 16 instructions.
The other feature that I implemented is a simplified direct map cache. I implemented this because it takes about 5 to 6 instructions to read from memory. It takes a long time. Therefore, to speed this process up in the future, I implement a cache. I implement a 64 index cache.
So right now a demo of my program. As of right now we are suspended, where you have the clock suspended with this switch over here, the second from left to right. We have the cache enable, the fourth from left to right, and then we can step through using the second push button at the moment. So let's run it, and as we can see, we're stepping through memory really fast. The leftmost red LED signals a hit on the cache, so when it's asserted we have a hit. When it's not, then we do not have a hit. So right now it means that the cache implementation is actually we could say successful, because we have more hits than misses. And then we can see the program over here printing out the line. The only thing is that the program is not fast enough. I mean, it's faster with the hardware multiply and with the cache implementation, but it still is not fast enough for a user to use. So as of right now, the program is requesting an input from the user. So let's input -3. And then as we can see over here, we got some misses and some hits. Also, some more functionality that we have is these 4 hex displays. They show the current instruction. Then the next 2 show the current state, which is actually moving really fast. If we push the switch button up, the left one, the leftmost to the left, it displays the current PC. Also, we can see the registers by pushing the 4 rightmost switches. So we can see register 1 on the 4 left hex displays, register 2, 3, 4, and then after providing the first integer and the second integer, we will get the product.